All right.
language that they have on crayons. Like 5 languages on.
Well, let me get started.
I did like that.
So I'm going to start. Yeah, Father, we thank you for this day. Thank you for this class and the lively friendships that are going on here. Pray that you'd just guide our steps, help us to glorify you what we do, and understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So today, so there's something missing from my notes, obviously, which is chapter 5, if you've been looking. And I'm working on typing those up right now. I'm not done with that by any stretch. However, the chapter 5 that's missing is largely contained in my old lecture 15, which is a handwritten PDF. So if you want to, you can look at that. I should have chapter 5 posted, sometime in the next few days. But so today I'm going to talk about multivariate calculus for a bit because it matters, and we should just have a talk about it because we're going to use it. So let's do that. And so multivariate calculus, there's two parts basically that we're interested in. The one is differentiation, the other is integration. So let's talk about differentiation to start with. The basic ideas we need are partial differentiation. All right, so partial differentiation is what I want to talk about. And rather than giving you a definition like I might in a math class, I'm just going to give you examples. All right, and I think if I give you examples, I'm pretty sure you're going to get it because partial differentiation is not hard. So let's look at some examples. Example 1. If I am calculating the partial derivative with respect to x of, let's say, x squared plus y squared, for instance, the way this works is, and by the way, so first of all, this notation is not a d, this is a partial, all right? So that's a notation for a particular kind of differentiation. And what this means, what the partial differentiation means is that we're treating, we have a function, we have an expression which has more than one variable, all right? In this case, my expression has variables x and y. If I write partial x, then what I mean by that is a differentiation with respect to x holding y constant. In the back, please close the laptop. Thank you. So, so this is 2x, all right? My apology, my 2 sometimes looks like my partial. This is coincidental. Yeah? Oh.
What's the character that you're using for the partial?
It's called partial.
It's its own.
It's its own thing.
And all of
Yeah.
those ones on the bottom are partials.
These are all partials. Partial x, yeah.
Can you only do partial when it's being added? Like, can you do partial if it's being multiplied to each other?
We'll get there. So this, by construction of partial differentiation, is 0. If we have, so like the basic results with partial derivatives are like these. Partial x, partial y is 0. Partial y, partial x is 0. Partial x, partial y. Do you guys want to guess what those are? 0? No, not everything. If everything was 0, this would be very easy.
1?
But not particularly interesting. Yeah, 1. 1 and 1. All right. So the answer here to my first example was just twice x. You asked me, can we do products? Sure. For example, if I was to say partial derivative with respect to x of x times, y to the power x, we could do that even. So in this case, we do a product rule. We've got partial x times y to the x plus x times partial x of y to the x. All right. How does that simplify? Partial x is just 1, right? And so what we get here is 1 plus, I still got a y to the x there, right? So my first term is y to the power x plus x times what? What is the derivative of y to the x? Let me show you what this is. You don't know? Yeah, that's fine. Let me show you something with different letters, maybe to give you an idea. If we had d dt of a to the power t, how would that go? See, we're varying x, and the base y is held as a constant. So this is an exponential function. So just like this gives me natural log of a times a to the t, in the same sense, over here, I get what? I get natural log of y times y to the x, because it's an exponential function in this sense, right? So partial differentiation with respect to x means we're varying x, holding all the other constants fixed. That's the way this works, all right? All the other variables fixed, rather. Oh, yeah, so here's another example, just to show you a difference. If I was to say calculate partial x of partial y of y to the x, how would that go? Now, notice that we're taking the derivative with respect to y. The base is the variable, right? This is like what? By analogy to like functions of time, this is like what? This is like d dt of what? Maybe like t to the n, right? We know how that goes. N t to the n minus 1, right? So that's the kind of we're varying the base, right? This is a power function. The derivative of a power function follows the power rule. Here, the power is x. So the answer is x y to the x minus 1. All right? Example 4. Guess I'll put it up here. What do you guys think would happen if I had, say, partial x of e to the xyz? How would that go? You're like, z, wait a minute. I thought we were just doing x and y. No, we could also do x, y, z. All right? If I have an expression with x, y, z, I'm thinking of x and y and z in this context as being independent variables. All right? When I calculate that partial x. So guess what? There's a chain rule. So how do we differentiate the exponential function? You guys know the drill. It's the exponential of the inside function, which in this case is xyz, times the derivative of the input, which the inside function, which here is xyz. All right. So how's that go? Well, this is e to the xyz. And so here, if we're taking the derivative with respect to x, we hold y and z constant. Y and z are constants. We can pull them outside the derivative, right? So this is really partial x of yz. In other words, the answer here is simply yz e to the xyz. All right? So I think if you search your heart, you'll realize you already know how to do this. We do this in Calculus 1 already, right? Like we ask you differentiate with respect to a, or holding x, sometimes we're like a is the variable, differentiate with respect to a rather than x, You've seen these problems, even in Calc 1. You know what I'm talking about? They have like x to the a, calculate the derivative with respect to x, or calculate the derivative with respect to a. I see this problem in Calculus 1 even. So in short, partial differentiation is just regular differentiation where we think of the other variables that are on the scene as being constant with respect to the differentiation. That's it. And I can define this in terms of limits and stuff if that would make it better. But I think we start to understand, right? So being that you're not totally confused, I should introduce something else to confuse you. That's my job. So definition, if f is equal to a function of x and y, then the gradient of f, or nabla f, is equal to partial f, partial x, partial f, partial y. By the way, we can give a more abbreviated notation for this if you like. We could just do like partial sub x of f, partial sub y of f. Sometimes I like that notation because, you know, why write two partials when you can get away with just writing one? So this is the so-called gradient of f. Gradient of f. Now, if on the other hand, you have f as a function of x, y, and z, then the gradient of f is defined to be partial xf, partial yf, partial zf. So the gradient of a function of two variables is a two vector. The gradient of a function of three variables is a three vector. All right? Now you might wonder, what does this mean? Like, what is the gradient? Why are we talking about this? Well, I wouldn't be talking about it if we didn't need to understand it in order to really tell the story of energy. The reason I'm doing all of this in here is not just because I love calculus, although that's true. It's because to give an intelligent answer as to what mechanics is and what the conservation of energy means, we need this calculus. Okay, so I really didn't answer what the gradient is, and I won't fully answer that question here because that's a question for calculus 3. But nevertheless, whether or not we fully understand it, we can calculate it. I can tell you what it means. What it does is it tells you the direction in which the function is increasing at the point. So like, for example, if I have f of x comma y is equal to x, or if I have f of x, y, z is equal to z, let me call this g to give a difference. The gradient of f, what is it? What's the gradient of g? So we have the partial derivative of x with respect to x is 1. Partial derivative, I did it wrong. What? See, guys, look at this. What am I supposed to put here? I'm supposed to put not, I'm supposed to put not y, but x. Yeah, sorry about that. Did I do that down here? No, I got z, z, z. All right, cool. So, so I get 1, and this is 0. This here, I've got 0, 0, 1. Do you see what I'm talking about? So this is the direction in which x increases, right? Down here, this is the direction in which that vector points where? In the direction in which z increases. This is what the gradient does, is it points you the direction you need to go to level up. This is more exciting, of course, if we look at a function which is not just stupid like these. You know, like, how about this? If we look at f of x comma y equals to x squared plus y squared, this is a kind of interesting function. What's its gradient? Well, the gradient of f is what? Partial x of x squared plus y squared, partial y of x squared plus y squared. That, my friends, is 2x to y. So one of the things that you need to start adjusting to is the idea that we're not talking about a single vector here. We're talking about what? A different vector for each choice of x and y. So when we take the gradient of a function of 2 or 3 variables, it gives us what's called a vector field. All right, a vector field is not a single vector, it's an attachment of a vector at each point in the space. So like if I draw a graph of this, I can. How do you graph x squared plus y squared? It's a circle. Now, what is a circle? If you set it equal to a constant, right, it's a circle. Agreed? So this kind of plot in calculus 3 is called a contour plot because these are contours, level functions, level curves actually, right? Maybe this is radius 1. I guess this is technically radius square root of 2, square root of 3, whatever, you know? I have, oh, my bad. Just a second. I should put, I'll get it eventually, guys, here. So if this is the circle of radius 1, circle radius 2 puts x squared plus y squared equal to 4, right? So, I'm sorry, guys. I need to, I just need to write what I'm doing. X squared plus y squared equals to a constant, right? If I label these curves by that constant, this is c equals to 1, this is c equals to 4, right? This is c equals to 9, perhaps, if this is radius 1, 2, and 3, respective. All right. Anyway, my point to you is to understand a function of 2 variables. One of the things you can do is you can draw level curves of it, right? And those level curves kind of describe how the function behaves. Probably it kind of reminds you of like a topographical map, right? Where you look at the altitude of the terrain, right? And you have these little lines, and those lines tell you sort of, you know, constant altitude curves, right? You can kind of see where the mountain raises up and lowers down by these little curves. This is a topographical map. This is a mathematical analog to that. You can imagine these kind of lifting up out of the board, if you like. If you wanted to graph z in your direction, that would give you z is equal to x squared plus y squared. That'd be like a paraboloid. But anyway, I am now drifting into calculus 3 land, so let me stop. But the gradient field we can draw if I just pick a point. Well, I regret too much detail on that one. So if I just do, here's like, you know, 1, 0, minus 1, 0, 0, minus 1. That's supposed to be a circle. 0, 1. And then I graph the gradient. Where does it point? Gradient of f at 1, 0 is what? Two, 0, right? Gradient of f at minus 1, 0, where does it point? Negative 2, 0. Gradient of f at the point 0, 1, where does it point? Yeah, 0, 0, 2. And find 0, 0, minus 2, right? So if I plot those over here, they look respectively like this, that, and that. Not to scale, right? If I did it to scale, it should be twice as long as the distance from the origin, right? Because if that's the unit circle, it is. These vectors should all have length 2, technically speaking, right? But you can see that if we go follow the gradient vector, we're going to the larger values of the function. This is the meaning of it, all right? We do want to have some understanding of gradient because we're going to understand taking the gradient of a function corresponds to something about potential energy, which is, of course, physically interesting, right? Okay, so that's just a crash course, and that's what the gradient is. This is how you calculate it. It's kind of what it means. It points in the direction of leveling up. Don't ask me to draw the picture in 3 dimensions, right? Because in 3 dimensions, you're talking about an assignment of a vector at each point in 3-dimensional space, all right? So, listen, there's all kinds of more things I can tell you about the gradient, but I think that's a good place to stop talking about just differential calculus at this point. I will introduce whatever else we need as we go on, okay? So at the end of the last video I asked you guys to watch, I started talking about work, right? And so what is work, right, is the question. And I ultimately gave you a definition for the work done by a vector field, right? Or, well, the work done by a force, I should say. The work done by a force field. So I'm going to start with that definition. And, oh yeah, I just need to check. I had this feeling about my mic not being turned on. But, yeah, whatever. It's bouncing. Cool. All right, so. Whew, here we go. So the definition, given force field F and an oriented curve C, parametrized by r vector of t for, let's say, t1 less than or equal to t less than or equal to t2, we define the integral of f dot dr is equal to, here's how it goes, over the curve C. It's the integral from t1 to t2. We take the vector field, we evaluate it at the path r of t. Then we take the dot product of that with the velocity of the path, namely dr dt. And we integrate that over time. This is called the line integral of f over the curve C. This defines for us the work done by f, the work done by f over C, right? This is the work. So I should emphasize here, guys, that C, it looks something like this. It's going from the point r of t1 to the terminal point r of t2. So this curve is an oriented curve. It has a direction, right? This is the curve, something like that. Notice that I haven't told you if the force is a two-dimensional force or if it's a three-dimensional force or a one-dimensional force. It could be any, and this definition applies just the same. So before I go on, it's helpful for us to actually kind of reformulate this integral a little bit using some of the other math we talked about already. You remember we talked about the unit tangent? Remember that? So we have the velocity is equal to the speed times v hat, right? But our other notation for that was v times big T, right, for unit tangent. And here, v is what? It's ds dt. You can work that out. If you differentiate the arc length integral with respect to time, the fundamental theorem of calculus shows you that the integrand of the arc length integral must be the instantaneous rate of change of arc length, but that is exactly the speed. So speed is ds dt, where s is the arc length traveled, the distance traveled. And as such, I can rewrite this here as this. I can rewrite this as integral from, say, t1 to t2 of f of r of t dotted with, well, big T times what? Times ds dt. I'll put that over here, dt. So it turns out that this is yet another integral. This is called an arc length integral. And by definition, what I have above is actually the integral over the curve of f vector dot t ds. And this, in some sense, is a very good geometric description of what this work integral is. So another name for the work integral is, this is also called the circulation of f. or the circulation. Although when we say circulation, that kind of tends to be honest, in the context of physics, right? When we're thinking of F as being a physical force, we don't oftentimes say circulation as much. Circulation really is more, for example, if you had the vector field that you were integrating was actually a velocity field for a liquid, then this literally would say something about the circulation of the liquid. But if you look at this formula we have, geometrically, you guys tell me, what would happen if the force is perpendicular to the tangent vector field to the curve? What would that mean? If the force is perpendicular to the unit tangent, what would that say? What's F dot T in that case? What's that? No, I said, what if the force would be in the normal direction? Good, yeah, that's possible, I suppose. But what I'm looking for here is it's just a formula. If F is perpendicular, if F is perpendicular to the unit tangent, then what? What's that mean? F dot T is what? 0. So, before we even do any kinds of fancy calculations, we can say something physical about this, which is that if your force is always applied perpendicular to the motion, it can't do work. So perpendicular forces don't do work because a perpendicular force has F dot T equal to 0 along the whole curve. If that's the case, it doesn't do work. Like, if I could have found my yo-yo before class, if you could imagine spinning a yo-yo, right? The tension force from the string on the yo-yo doesn't do work as long as that is radially applied to the circular motion, if you could imagine that. All right, so as a pragmatic matter, this is sometimes geometrically helpful to understand things. In fact, let me work out a physics problem that is best done with that notation, yeah? So, so the force fields that I wrote, like all of the gradient vector fields I just derived in the previous examples, what's the time dependence of these fields? Is there a time dependence to my gradient fields that we calculated today? Not unless you take a very meta perspective and say, well, you drew it on the board at 220, so no, that's what I'm talking about. In the formula, there's no time dependence, right? So these are what are called static vector fields. A static vector field is one which is independent of time. This definition makes sense whether or not the vector field is static. The issue is, if I stated this more carefully, what we need to know is that the curve is in the domain of the vector field. Whatever this vector field, it has to be defined along the curve so that I can actually calculate this, right? If I can do that, I can calculate the work. I say parameterization here, but in physics, really we're thinking about the particular physical trajectory that's involved. We're asking what's the work done, right, by that force as an object travels along that trajectory. This is the work done. Okay, so the interesting thing is in Calculus 3, the only thing we do is look at static vector fields. The concept of a time-dependent vector field is completely absent from Calculus 3. We don't care about that there. And here, sometimes we deal with static vector fields. Sometimes we deal with dynamic vector fields. Sometimes we deal with vector fields that are only defined in as much as the physical situation, only defined with respect to the physical trajectory itself. For example, friction. We could think about the force field defined by friction. We could calculate the work done by friction over some path in the plane. If you asked me, well, what's the friction force field at places other than where the object is moving, it wouldn't even be a meaningful question, right? So let me do that example actually. If I can draw a picture here. So example 7. So here's a plane, right? That's supposed to be a plane. And if we think about, a box, and Mr. Top Hat perhaps is pushing the box around, and the box travels some path, all right, which we'll call C. So it starts at this point, ends at that point. If this box has, say, mass m, right, we could draw the free body diagram at kind of an arbitrary point. What's going on here? We got the normal force going up, right? We've got force of gravity going down, right? And this is not part of the free body diagram, but geometrically, there is some direction which is the direction of motion, right? That's where big T points, the tangential direction. Or if you like, V hat, right? The unit vector in the velocity direction. Where is the friction force in this situation? Opposite of the motion. So it's diametrically opposed to the T vector, right? So this is my friction force. So what's the formula for the force of friction? The force of friction as a vector, right? It's mu sub k, I guess, because this is probably kinetic, right? I mean, we're moving. So mu sub k mg, because the normal force is mg, right? And that's the magnitude of the force. What's its direction? Opposite of t, right? So to give it a direction, we should multiply this by what? By minus big T, right? That describes the friction force. So now we can calculate what's the work done by friction on this box of mass m if Mr. Top Hat moves it around this curve in the plane, all right? And why did I do the plane and not like a hilly valley or something? If it was a hill and it had bumps and stuff, then I'd have to really work a lot harder, because then the normal force would be varying and I'd have to take out the part of gravity. It would be just much more complicated, right? So plane makes it easy in the sense that the magnitude of the force of friction is always just mu sub k mg. It's just that the direction is going to be changing because the motion, goes in different directions. So anyway, let's get to it. So what's the work done by the force of friction? The work done by friction is the integral over the curve of the force of friction dot dr by definition of work. Now, how do you actually calculate that? Well, that's the integral over the curve of mu sub k mg, right? Let me pull the minus out to this thing here and just leave us a t, right? Dot what? I'm going to use this formula right here. I'm going to use the easiest formula. Let's not make it more complicated than it needs to be. We can use this formula. Makes it really, really easy. So for this problem, f dot t. So I've got my f. This is f. And now I'm supposed to take the dot product with t. It's kind of dumb, but there it is. So what is this? Well, this is mu sub k. My bad. Pull a minus out. So pull a minus out. We got minus mu sub k mg, the integral of ds over the curve. Because t dot t is what? T dot t is 1, right? T is the unit vector, it's the unit tangent. What's the integral of ds over the curve? This is something you might have calculated in like calculus 1, maybe calculus 2, I don't know. What's the integral of ds over the curve? It's not a trap. Like I'm asking an honest question here. Do you guys know?
It's just S.
It's just s. But what would s mean? S. What is s?
Is that the distance?
Yeah. So this is minus mu sub k mg. I would use maybe L of c for the length of the curve. The arc length, right? So the work done by friction is simply the length of the curve times the force of friction, and it's negative because the friction force is always applied exactly opposite the motion. Does that make sense? If you had high school physics and you already thought about what is the formula for, what's the most naive formula for work? Where do we start? What's our starting point? Like I did the last video I asked you guys to watch. Force times distance, right? Oh, I guess it's even more elementary than that. So, excuse me, that's even more elementary. That's like force times distance, that's like middle school, right? High school maybe is vector dot displacement, right? Vector dot displacement gives you the work done. Oh, you guys are right. What am I? You're not wrong, you guys said. Let me stop correcting you. Recap. Work. Force times distance is one thing you probably first learned, right? Force times distance. But it's also, or force dot displacement, right? Or it's the integral from a to b, f of x dx. Now each of these formulas has their place. You guys tell me, what's the fine print in each one of these cases? If I'm going to write work as force times distance, what are we talking about? We're talking about a constant force, right? In what? One dimensional. This, we're talking about constant force, right? Over, line segment. And how about this? What's the deal here? One-dimensional force, right? One-dimensional force what? Does it have to be constant, though? No. Possibly variable. All right? So this definition of work I wrote at the start of class here today, middle of class today, it addresses all of these different cases as special cases. It allows for the possibility that the force is changing direction. It accounts for that. It allows for the possibility that the physical motion's not just over a line segment, it's over a curve. It accounts for that. This is the general definition of work. This is what we need to understand work is in the abstract. But I know I like this example in the sense that it allows me to showcase why this very geometric and nice description of what work is actually useful for solving a physical problem. Because if I tried to find formulas, like explicit formulas for the motion of the box and the plane, it could get kind of complicated, right? But we can see the calculation just like that. Another example I should probably do. Actually, before I do any further examples, I probably should actually show you guys why this all matters. We will do more examples of like calculations of work and so forth, but I want to see if I can derive the work energy theorem for you guys today before I forget. Can I erase this stuff here? Is it fine? Yes, no, maybe so. All right. So, let's see this. So here's the work energy theorem. All right. If the force is the net force, then the work done by F along a path from, let's say, R1 to R2 is given by the change in the kinetic energy. All right, so let's introduce kinetic energy. The kinetic energy, K, is equal to 1/2 mv squared. This is kinetic energy. Now you might wonder, why do we care about kinetic energy? Well, this is one reason, because the kinetic energy tells us something about the work, all right? All right, so let's see here. I mean, this is part of a long discussion. It's not going to be finished today. It takes us like about 2 or 3 classes to really complete this thought entirely. So, hang with me here. But here it goes. So the work done by the net force, right, is the integral along the curve that goes from, let me call this curve that goes from vector R, from point R1 to point R2, right? Like that. And, all right, so we're calculating the work done by the net force. Now that, by definition, is the integral from, say, time 1 to time 2 of the net force at R of t dot dr dt dt. I regret writing that because that detail wasn't really necessary. I really should have got to the point of this, is what makes the net force the net force? Like, what is net force? What law did we learn about the net force as it relates to acceleration? Do you guys remember? Yeah. So net force gives us Newton's second law. The force is equal to ma, which is equal to m dv dt. So this is m dv dt dot v dt. But there's a simple calculus identity here that we should notice. What happens if we differentiate the velocity dot itself? What happens then? We kind of did this kind of calculation a little bit ago. Remember product rule? So I got dv dt dot v plus v dot dv dt. But since the dot product is commutative, that gives me 2 dv dt, 2 dv dt dot v. I can't say words. So look what I have. See, I've got this right here, right? So what can I can trade that for a what? Looks like 1/2, right? ddt of v dot v. Do you guys see that? Are we good? Can you guys tell me how I can pull the m over 2 inside the expression, right? So I can write this as the integral from t1 to t2 of the total derivative of 1/2 m. What's v dot v? Let's write it as v squared. That is what it is after all, right? What is v dot v but v squared, right?
Why can we assume v dot v from just dot? Because right there we have just m dv over dt times v. Why is now you're expanding?
Over here. So we looked at the derivative of v dot v, and we found that that was equal to twice dv dt. So if I divide by 2 to the other side, it's an identity. I got to take this 2, divide it over here. What's in red is equal to, this equation over here shows you that 1/2 ddt of v dot v is equal to dv dt dot v. So that's why I replaced dv dt dot v with 1/2 of ddt of v dot v. But of course v dot v is just v squared, right? Any vector dot itself is the magnitude squared. The velocity dot the velocity is the speed squared, right? So now what do I have? These are the nicest kinds of integrals to do, right? If you have to integrate a derivative, what happens? They just cancel out, and we have fundamental theorem of calculus part 2, and we get 1/2 mv2 squared minus 1/2 mv1 squared, where I'm supposing that you had like v1 here and you had v2 there. These are the respective final and initial velocities. This is, of course, the change in the kinetic energy. So I use kinetic energy, like, don't tell Dr. Boudreaux this. He doesn't like this notation, and I lose respect from him whenever I use it. So don't tell him I used it. But I use KE for kinetic energy personally because it was taught to me in community college, and I just like it. It kind of takes me back to a simpler time. Did I ever tell you guys about my community college? So one of the great joys of my community college experience was I had a professor, and he'd drink Pepsi when he was teaching. And I was like, I didn't really think much of it, and then I started paying more attention, and I said, the bottle fills up. The bottle fills up when he's teaching.
Oh, okay, I know what's happening.
Yeah, that's right. Some of you know what's happening. And that was after the tobacco policy came into play. I love that place. Anyway, next time I will calculate more work for you guys, and we'll hopefully introduce potential energy. So, thanks everybody. Have a good weekend.